Okay, thank you, Andrea, for the introduction. I'm Gabriele Cazzulani, and I'm a mechanical engineering as background, coming from Politecnico di Milano, in Italy. And let's say I belong to the group in our department that works, let's say, in general on dynamics of mechanical systems. My background originally was like more in control engineering, mechatronics, and then I moved to metamaterials, always related with the idea of controlling vibrations and so wave propagation, said in another way, into mechanical structures. The presentation that I will do today is related to the work done by my colleague Emanuele Riva and me, mainly in the last years, with an overview of some, let's say, activities having a common framework behind, and with, let's say, more reference, more attention, at least in the presentation, to experiments and to experimental activities that we did on these specific kind of systems. So this is something I already said. We refer in particular to metamaterials for wave propagation and vibrations in mechanical systems. So our aim is to study, very generally saying, what is let's say, exotic phenomena, new phenomena related to the use of metamaterials to govern how vibrations propagate in a structure. So the application is always related to that. So among all the possible applications and possible fields of metamaterials, also not only mechanics, but also in many other physics fields, we focus specifically on this one. And in particular, in this presentation, I will focus on the activity that has been done referring to systems that are in general time varying, which means properties of the mechanical system vary over time in some way. I did this distinction between time varying and state dependent in the sense that with time varying I mean some modification of structural parameters, one or more structural parameter that is dependent on time and in some way predetermined with some law. While with state dependent, I intend, due to my background with active control systems, the use of some active control, so some modification of the behavior of the system that is dependent on some measurements or on how the system is behaving, on what the system is doing in real time. In this presentation, I will focus more on time varying. That is an activity on which we did many different experiments and many different analyses, with some final hints about some perspective and some activities we are doing also on active controls, on feedback control metamaterials. Talking about this kind of time varying metamaterial, of course, one of the main issues is how to do them, because, okay, numerically it's, let's say, easy in some way, to introduce variations and modifications in the law and in the parameters of the system, but then, okay, you need to have some way to implement it in practice. And in this sense, we found that the use of piezoelectric actuator is very useful because they are very flexible, they have a good electromechanical coupling, and so it is quite easy to govern the mechanical behavior through actions given on the electrical side. That is much more easy with computers, controllers, and so on. So in this presentation, I will first give a very quick outline, recall on piezoelectric devices, just because I'm not sure everyone in the audience is familiar with them. If you are all familiar, I can skip this part. And then I will show some implementation of time-dependent structures with some applications and results. So talking about piezoelectric actuators, they are materials and then actuators, transducers. They are materials based on a coupling between the mechanical world and the electrical world. This is the notation that is typically used talking about piezoelectric, that is different from the classical mechanical one because it's more the electrical notation. Basically, the idea is that if you move the piezoelectric material or applying a stress or a strain in the mechanical field, you get some behavior also in the electrical field and vice versa. This means that depending on how you command the piezo on one side or on the other side, you can obtain many nice effects. And how strong is the coupling between the electrical and the mechanical world is governed by this constant called K-square, that is between 0 and 1, and is a sort of efficiency of the energy transmission between mechanical and electrical field, and vice versa, because the effect is reversible. So these piezos can be used as sensors. If the input is on the mechanical side and the output is a measurement on the electrical side, they can be used as actuator in the opposite way. So I command the piezo with a voltage source and I obtain some behavior on the mechanical side. And so this is very interesting for active control, of course, because I can both sense and actuate. And they can be, let's say, used also by applying a shunt, so some circuit connecting the two electrodes of the piezos. This represents the most simple circuit that you can apply, so open circuit and closed circuit, so infinite and zero resistance basically. And what you can find by rearranging the equation is that this change of state on the electrical side modifies the stiffness of the system on the mechanical side. So the open circuit, that is this one, is much rigid than the closed circuit, that is this one. Consider that the axes are reversed, so this is force and this is displacement. Another way in which you can govern this piezo is through shunts, that is circuit connected to the two electrodes, and again based on the equation of rearranging again the characteristic equation of the piezo and applying the circuit on the boundaries on the electrical side, you can come out with this formula telling you how the Young modulus, so the stiffness in the end of the piezo, changes with the variation of the equivalent impedance on the circuit that is attached. So in this way you can govern in a frequency dependent way also what is the behavior in terms of equivalent stiffness of the structure. Among all the possible shunts, what we are using more in this specific framework is a negative capacitance shunt, that is a shunt designed to behave as a negative capacitance. Of course, a negative capacitance is something that cannot exist in nature, as many other negative things, but that can be, let's say, achieved through a proper electrical circuit designed to behave as a negative capacitance would behave. This is a scheme of one of the possible implementation of this circuit, and you have to notice some important thing. First of all, okay, you have the formula telling you how much big, let's say, is the capacitance. We have to pay attention to a couple of things. First of all, that a negative capacitance inside an electrical circuit is a possible source of instability, so not all the values are allowed for the negative capacitance. But also on the mechanical side, if you look at the plot on the right, the equivalent Young stiffness of the piezo compared with the original one, so the one without the circuit, can go below zero with some values of the capacitor. So you have to, let's say, stay away from these ranges with possibly a reasonable margin, because if not, the system becomes unstable. But if you remain in the stable region, this effect is interesting because basically it's like increasing the difference between these two curves. So when you shunt on a piezo, it's like taking one of these two curves and moving away from the other. So like increasing the electromechanical coupling of the structure. So in some way you can increase the efficiency of the system. So after this introduction, what we want to do with this kind of systems? What we want to do is to study in general systems that are in some way space and time modulated. Okay, space modulated is something that is typical in metamaterials. Time modulation is something we want to achieve using this kind of system, because we know that from literature that space-time modulation is something that causes some very interesting properties in metamaterials. So this is basically a scheme about how we implemented this also in practice. So you see a beam with piezos attached as close as possible one to the other, each one connected, or each pair connected to a certain circuit and a switch. So we can switch from open circuit to closed circuit with negative capacitance in this case. In order to achieve a generic time response, okay, we simply have to command the switches in some way. But if we want to obtain a specific time response or a frequency time dependent, we need to command the switches, of course, with a coordinated way. So they have to be driven so that their behavior is coherent with a certain behavior that we want to achieve. In particular, talking about space-time dependent systems, that is like this one, in which the properties of the material change both in space and in time simultaneously. Let's say this is a plot about how the properties of material could be in one cell, in theory, so with a continuous shaping. That is something we cannot achieve in practice. What we achieve in practice is more like this, so discrete in space and hopefully continuous in time, or even more than this, so discrete in space due to the cells, and discrete in time due to the opening and closing of the circuit. So one thing that we did first is to develop a generalization of the classical method that is used to analyze this system in order to be able to address not only the theoretical case, but also the practical case that is that one. And then once we did all the simulations and all the analysis, we did also the practical implementation of this system, as explained before. Notice that the system is made by many piezoelectric patches attached on the beam. There is a patch at the beginning that provides the input, so the input wave crossing the structure, and then the patches are can be modulated in different ways. This is a preliminary test that we did just to check the behavior of the system in open circuit, closed circuit, and like with a freezed time modulation. Okay, so you see that the red and the yellow represent the open circuit and the red patches represent the closed circuit. Okay, so in a freezed situation. And what happens is that giving a certain input and doing the 2D Fourier transform, you see that the behavior is what expected. So the dots are the numerical and the colors, let's say, are the experiment with a band gap that is clearly visible in the region between like 9 and 10 kilohertz. What happens if we apply also a time modulation to our patch? So time modulation means, as I said before, that the patches are governed by in the cell, like in this way, so with a certain phase shift in the modulation between one patch and the next one. In particular, to achieve directionality of the modulation, you need at least 3 patches consecutive to create a unit cell that are shifted by, if you want to do symmetric, by 120 degrees. Because if you take 2 cells shifted by 180 degrees, you have time modulation, but you don't have directionality. Because if you reverse, it's the same. So this is our unit cell. From this unit cell, we computed the numerical response of the system, and then we compared with the experiment in the freeze case, so without time modulation, and in the modulated case. Here you can see 2 different modulation frequencies. This is for 1 kilohertz modulation of the patches on-off, and this is for 3 kilohertz. Of course, increasing the modulation, what happens is that the 2 band gaps for waves traveling to the right and waves traveling to the left become shifted in frequency, and so you achieve what is called unidirectionality or a mechanical diode. There are many ways to call it, but in the end, the idea is for some frequency ranges, waves can propagate in one direction, but cannot propagate, ideally, in the other direction. Or practically, they propagate in the other direction, but with a strong attenuation. Of course, you see, again, the dots representing the ideal dispersion relation zoomed around the region of interest, and with the color maps, you see again the 2D Fourier transform that you have before and after the modulated part. So the wave that is in some way, that you have after the modulated part, which means that given a tone burst as input, so something including all the frequencies in this range, what you obtain on the outputs on the other side is this kind of behavior. If you reverse the modulation, you can do the same in the opposite direction and get the other figure. Same for 3 kilohertz, which is exactly the same, simply with a stronger directionality of the wave propagation. So after this result, we went on. This is something we published some years ago. We went on to a different kind of formulation with the aim, again, of using the same structure, so the same experimental layout in some way, to achieve, with just few modifications on the electrical side, very different mechanical behavior. So this is one possible behavior that we can achieve. The second one is, that we studied, is what we call the adiabatic wave pumping. Wave pumping means, is called in this way because it means that by properly modulating some properties of the structure, you are able to inject a wave on one side of the structure, and then after some time, or some space in this case, because this was a work only passive on a 2D structure, the wave basically is transferred on the other side of the structure. And this can happen in some particular frequency ranges. Due to that particular behavior you can see in the dispersion relation, that occurs when, due to the boundary condition of the structure, when one mode, depending on the phase of the different cells, becomes localized on the left side or right side of the structure, or on the bulk, like in the point named as 2. So varying the phase, this is a structure in which, I don't know if you can see, but the periodicity along the y direction is not always the same, but is varying slowly. What happens is that for some phases, depending on the boundary condition again, for some phases, that mode is localized on the left. For some phases, that mode is localized on the right. And for some other phases, the mode is a bulk mode, so involves all the structure. So you see, for some, that mode changes frequency, and for some phases is in some way tangent to the bulk zone of the dispersion relation. So what happens, was in space, so we wonder, okay, we can do the same in time. The idea is, yes, theoretically, we can do the same. How? By doing exactly the same thing that has been done in space. So by modulating the phase of our different unit cells in terms of, in this case, stiffness, in the same way we said before. Okay, so by changing slowly the phase from the beginning to the end, we are able to do the same. Which are the issues that we have to face? The first issue is that we need, or that is the last in this list actually, but that we need a continuous change, because we need a slow change, a smooth change, that is, okay, mathematically called adiabatic, which means that we cannot use just a switch on-off, because of course it's not smooth. The other challenge, that is the other 2 points that are connected, is that due to the fact that we need an adiabatic, so slow transformation, we have the problem of damping. Because of course damping in a real structure is significant, even if it is quite low, like in the structure we consider, because if we need a slow transformation, we need a long time, and a long time means a lot of periods and a lot of attenuation. So we have to face in some way the problem of damping. Why this? Because if we do not do this adiabatically, when the mode, as in the curve we said before, goes closer to the others, what happens is that the energy, let's say, shifts to the other mode, and so doesn't remain on the wanted one, and so you don't have the pumping effect from the left to the right. Okay, this is just the same model done on our beam with the mode that specifically for our beam with our design changes this phase, this behavior changing the phase. So you see here the 3 modes corresponding to 2 different phases of the piezo patches. How many? Okay. And okay, this is how we realized in practice, because the idea is, okay, now we cannot simply switch on and off as in the previous case, but we need to modulate the behavior. We need to modulate ideally continuously. Practically it will be, let's say, almost continuously, so with small steps. We need to modulate the stiffness of the system through the negative capacitance, but in a continuous way. And in order to do that, what we used in this case was a variable resistance that is included in the circuit, in the patch, in the circuit of the negative capacitance. And this variable resistance is a programmable resistance that can be driven through a specific command provided by a board. So basically this is, again, the same system as before, but with now this programmable resistance and with, okay, some picture about the instrumentation, so serial controller to drive these resistances, and okay, a scheme of the code that has been used. So this is again some test. This is a sort of preliminary test that is still interesting because it confirms also experimentally the fact that changing the phase of the different patches, you change the behavior of the system. Again, with the lines, you see the numerical values of the modes varying the phase. This is a picture with a spectrogram with an excitation on the left of the structure, and what you see clearly in a steady state, okay, point by point, so phase by phase. What happens is that if you excite on the left of the structure, that it corresponds to the dashed line, so left localization of the mode, you are able to excite that mode in this phase range, so when the mode is localized actually on the left, while when the mode is localized on the right, you don't see anything, so which means that you are not able to excite that mode, which is, okay, coherent with what we know. Of course, the other figure is the opposite, so if we excite on the right, we obtain the opposite, so we are able to excite the system on the right side, so when the mode is localized, for the phases for which the mode is localized on the right, but we are not able to excite it for the phases for which the mode is localized on the left, so it's the opposite of that. Besides this static analysis, we did the time varying analysis, so the transient analysis that is represented in this figure, where you see the length of the beam on this side and the time going on the other side. And here you see, let's say, a snapshot taken with 3 different speed of modulation that are all adiabatic in our sense. So what we do in practice is we have a first part of the story in which we excite the structure on the left side up to regime. Okay? After 12 milliseconds, that corresponds to the initial point of this picture, we start modulating the beam. Okay? And the modulation lasts this time period, so in this case 1 millisecond. And after the modulation of the beam, what happens is that you see that the vibration of the system becomes global at the central point, and then it is transferred on the other side. Which could be, let's say, interesting for applications in which you need to, in some way, control vibrations and to move energy from one side to the other side of the structure. And these are the parts that are more, in some way, completed of the work. Now I introduce some other possibilities that we are studying. This is very recent, but we did just, for now, as concept with a simple spring mass chain system. We have to move then to a continuous system and experiments. And the idea is to use basically the same system, the same layout to do what is called time modulation, pure time modulation, which means that I have a structure with some stiffness distribution. You can consider it constant everywhere for simplicity. And then after a certain time, you modify the stiffness of the structure. Modifying the stiffness means modifying the dispersion relation in some way. And so given the same wave number, modifying the frequency of the signal coming as output of the structure. These are some possibilities that can be achieved in 1, 2, or 3D with this kind of principle. For now, we are focusing on 1D. This is some results achieved on the spring mass chain, so a very simple system. Of course, if you compute the dispersion relation for different stiffness of the springs of the spring mass chain, you get a different dispersion relation. And so the ideal target is to move, let's say, from the blue to the red one, but without scattering. So without introducing some energy that is, let's say, drained away by a scattering in the other direction. That is the same mode, but in the other direction. Okay, here there is, I have to go quick, so I cannot enter into the details. Here there are some equation of the system and the condition for the adiabaticity, so how much slow must be the transition. And here there are some numerical results that we did with different transition. This is like a step transition, so very quick, of course non-adiabatic. And what happens is that, yes, you have the frequency conversion, but you also have some of the energy that is scattered back. If you reduce the speed of modulation, this effect is reduced, but we are still now in the diabatic case. If you go below the adiabatic limit, what happens is that you can achieve this frequency transformation in a continuous and smooth manner without ideally any reflection in the other direction. So you can transform the frequency of your signal from input to output. Of course, here we have still to do experiments, and I have finished conclusions. So to conclude, in this work and in this framework, we realized an electromechanical structure that can be used for wave propagation in time-varying structures, in time-varying conditions, and we achieved to, let's say, demonstrate also experimentally some interesting behaviors, some exotic behaviors of the structure. And all this can be done by simply, let's say, controlling the structure from the electrical side. As future outlooks, the idea is to go towards the implementation of active feedback, because active feedback, especially in some configurations, allow very interesting results. One is in terms of breaking the adiabatic limit, which means being able, at least again in theory, to do the transition in a faster way. That would be very interesting for the problem of the damping, because you are able to do theoretically the same as in the slow transition, but with a very, very quick transition, so without the problem of dissipation, attenuation due to damping. And the other one that could be interesting is the fact that with a particular case of feedback, that is the PTC matrix feedback, you are able to obtain very strange and very particular dispersion relations, which implies also zero or negative group velocities, which means that, okay, just to make, of course, that in theory at least you are able to like stop a wave in a certain position or govern the fact that the wave goes away or goes back or goes forward, depending on how the PTC metric gains are computed. Of course, this is just very preliminary, and there is a lot of road to go to experiment. Okay, thank you. Sorry for being a little bit late. And if you have questions, I'm here to answer.